Imagine the ultimate corporate fantasy. You clock out on a Friday, leave a complex problem on your desk, and return on Monday to find that a machine has autonomously finished the work, iterated on it, and optimized it while you slept. In early March, AI researcher Andrei Karpathy turned that fantasy into a 630-line Python script. He pointed an AI agent at his own training code, gave it a single metric to optimize, and went to sleep. 2 days later, the agent had run 700 automated experiments, discovered 20 genuine improvements, and cut training time by 11% on a codebase that one of the best machine learning researchers alive had already spent months polishing. This phenomenon scales beyond narrow machine learning applications. Shopify CEO Toby Lutke applied the exact same pattern to Shopify's internal data. His agent ran 37 experiments in 8 hours, yielding a 19% performance gain. Then, a startup took the loop and pointed it at agent behavior itself. An overseeing meta agent was tasked with rewriting a worker agent's prompts and orchestration logic overnight. By morning, it had hit first place on 2 major benchmarks that were previously dominated by hand-engineered human entries. This is what we call a local hard takeoff. We are not talking about an apocalyptic artificial general intelligence. A local hard takeoff happens when an optimization loop closes on a specific bounded domain, like a pricing engine or a fraud detection model, and compounds improvements autonomously, far faster than a human organization can track. Karpathy's agent found the bug because it could test hundreds of permutations without fatigue or context switching. Its effectiveness comes from an iteration rate that outpaces human researchers. Auto-optimizing training code works smoothly because the goal is narrow and easily measured. Point that exact same loop at a sprawling, vague business directive like optimize customer service, and the system breaks down immediately. To understand why, you have to treat the AI as a hyper-literal intern. It is an entity that will execute tasks at blinding speed, but it possesses zero contextual intuition and absolutely no common sense. Without rigid structure, this intern suffers from context rot. Because the agent lacks persistent, structured memory across sessions, it forgets its original objective. Every time it runs a new experiment, it reinvents the definition of success, leading to silent, untracked degradation of your systems. Wiring a self-improving loop into a chaotic, poorly structured corporate infrastructure doesn't solve your operational problems. It simply automates your failures faster. Safe auto-optimization relies on extreme environmental minimalism. This visual shows the architectural boundaries required to keep autonomous experiments on rails. It relies on the Karpathy triplet. First, restrict the agent to exactly one editable file. Second, define exactly one testable metric. Third, enforce a rigid time budget per experiment. Test and measure. By severely restricting the search space to this precise triplet, you turn a sprawling business challenge into a highly tractable brute force search. The hyperliteral intern is physically locked in a sandbox where it cannot wander off mission. A single AI agent cannot execute a specialized task and simultaneously grade its own performance. Doing both requires a split-brain approach. One node acts as the domain specialist, the agent doing the actual work. The second node acts as a harness engineer, a meta-agent watching from the outside to diagnose failures. If you give the meta-agent only a pass or fail score, it will immediately resort to metric gaming, introducing nonsensical mutations just to force the numbers up. To prevent this, you require traces, explicit reasoning paths outputted by the domain specialist. By analyzing these full reasoning traces, the meta-agent gains deep interpretability. Instead of guessing randomly, it sees exactly why the execution agent failed at step 14, allowing it to make surgical, logical edits to the code. This split-brain, trace-driven loop is the exact architecture the major frontier labs are deploying. Google DeepMind's Demis Hassabis noted recently that recursive self-improvement loops are an active pursuit across all top-tier labs right now. The business implication here is absolute. If your company is not currently capturing detailed reasoning traces from your AI deployments, you possess zero raw material for auto-improvement. Organizations relying on simple conversation histories and basic chat interfaces lack the technical foundation to manage an auto-improving agent deployment. Before you can run a Karpathy loop, you must build an evaluation harness. This is a rigid, isolated testing environment where hundreds of experiments can execute, break, and fail safely without ever touching your live production data. You also need strict version control. When an agent inevitably optimizes for a disastrous proxy metric, like technically resolving support tickets by simply hanging up on customers, you must have the infrastructure in place to revert the changes instantly. This reshapes the role of human labor. We are stepping away from manually executing experiments. Instead, our high-leverage work shifts to designing the constraints, building the sandboxes, and pointing the research in a profitable direction. Auto-improving AI does not eliminate human judgment, it concentrates it. The organizations that secure an asymmetric advantage over the next 2 years will be the ones that can most accurately define the word better, translate it into math, and hand it to a machine.